So I want to talk a little bit about the device physics of perovskite solar cells. And before starting, I want to acknowledge the colleagues and also professors at EPFL, because this work I'm presenting today has been done at EPFL in Professor Anders Schackfeld and Professor Michael Kretzel lab there. And I really want to come to the outline of this talk. So I want to discuss a little bit the evolution of perovskite solar cells, to give you a brief introduction. People working in this field, of course, know it, but it could be interesting for the students. Then I want to discuss some optoelectronic properties of this material, trying to give mainly also an introduction on what is important when we talk about solar cells. And then focus a little bit on recombination, because this is a loss mechanism, the dominant loss mechanism in perovskite solar cells when it is non-radiative. And then I would like to discuss a few more kind of peculiar cases of these perovskite solar cells and materials, which are due to these slow transient processes related to their mixed ionic electronic conductivity. So let's directly start with the introduction into the field. So we are, of course, interested in this research field because the power conversion efficiency of solar cells made out of these materials is very high. Here you see a chart of all best research cell efficiency. So you can see there is a plethora of different materials you can use, and you can reach also very high efficiency values when you make, for example, kind of tandem and multi-junction cells. What we want to do now, we want to zoom into this regime here, where you see emerging photovoltaics. And here you can see the line for these perovskite solar cells. So the first point was just a couple of years ago, and now we are already at values where it gets here really crowded. So you see the blue ones are silicon solar cells. So we are very close there as well, with a value of more than 25%. And this, given that this material is processed from solution very often. And yeah, what is this perovskite material? Well, the name goes back to this calcium titanide mineral, which was actually discovered in Russia in the 19th century. And then later on, and we're using, of course, this word nowadays for this ABX3 structure. And the perovskites I'm talking about, and these are those which are used in these highly efficient solar cells. These are lead halide based ones. And here, for example, so synthetic materials, here you have the cesium lead. X stands for iodide or bromide, for example. And the structure, if it is in a like ideal cubic one, it can look like this. So you have here the lead, and then you have here the halides, which are from this octahedra, and then you need to fill in this other cation, which is here this cesium, to make a kind of stable three-dimensional structure in this system. And further on in history, this cesium was then, for example, replaced by small organic cations, and then we are at our inorganic hybrid perovskite materials, which we are using nowadays in the solar cells. And these materials are not as novel as they are in the solar cell field, but they have been already investigated as semiconductors in electronics, actually, for example, by David Mitzi already quite some time ago. And then it took until 2009 until the first solar cell has been reported by Miyazaki Group. And if we then very briefly look into this time scale of the, let's say, early history of the solar cell until we could, let's say, reach around 20% efficiency, so from 2009 to 2015-16, we can see that it started with a route where we process the perovskite. We can just basically take the two salts, lead iodide and this methylammonium iodide, dissolve them, bring them somehow together, for example, sequentially or even in one solution, and then deposit a film, anneal it, and we can already form this material. And this was first done here in a disolar cell architecture, where it was used to replace the dye. This was very unstable architecture because there was a liquid electrolyte. This is here, this green part. Here would be the mesoporous titania, the blue one. So the major breakthrough was to make a solid state device. This was when this electrolyte was replaced by this pyrometad organic whole transport layer material. And from that point on, then already like 12% efficiency have been reached. Then more and more kind of the film deposition of this perovskite was engineered to go from this mesoporous architecture, which is also shown here in an SEM image, towards a more thin film-like architecture, which is this one here, which I will show a zoom very soon. Again, in this talk, I want to mention that this is not the only architecture you can make perovskite solar cells. In contrast to dye solar cells, where you in principle always need this mesoporous structure, you can make planar architectures where we have just several thin films on top of each other. And you can make, for example, this material by other methods than solution, for example, sublimation in vacuum. One of the next speakers, Henk Bolling, will give probably a talk focusing here on this route. Here you can see now the promised zoom. So this is how these devices, which I want to discuss the physics of, look like when we take a cross-section in the electron microscope and color a little bit the layers. So you can see here the core of our solar cell. This is the absorber, the perovskite material, nanocrystalline materials with here grains. There a thickness, here is the scale bar in the order of 0.5 micron. And this is sandwiched in between different layers. We will discuss a little bit their function also later. The titania here on the front side, the light would come here through this transparent conductive oxide here, which is, as the name says, transparent like fluorine oxide. And then we have here a whole transport layer. I already mentioned this organic molecule, for example, and here gold on top. And when you look at a photograph, you can see the gold. When you look from the back side, you can see that this material, this could be the methyl ammonium lead iodide or maybe a little bit more complicated mixture, looks already very black, so it's as promising as an absorber. And here is a little energy diagram. Such diagrams I will use during these talks then more often. This illustrates in principle how this solar cell works. So when you absorb here the light, this titania provides a condition so that the electron can be harvested here in this energy landscape, whereas the electron would be blocked here at this whole transport layer because there is a big energetic barrier. And this gives us a selectivity so that we get an electron in this direction and the whole should then diffuse potential drift also in this direction. This is very roughly how these devices could work. Now we directly want to go a little bit more into detail onto solar energy conversion. So what we want to do, of course, we want to convert the solar sunlight directly in our solar cell. Now here we just sketch the silicon device into electricity. And coming back to the very simple sketch of a semiconductor where we have valence band and conduction band states. Of course, we need to absorb the light. We excite electron from the occupied states into the unoccupied states. And then if you want to drive a photocurrent, as I just mentioned already, we want to extract them into different locations in space. So let's say the electron here and the hole there, and then we get a net current. So we need free and mobile charges. This we have in these perovskite semiconductors in principle directly upon absorption. And when we then operate this device, of course, it's not enough to just get current out. We want to get power out of this device, which means we also need to get a certain voltage out. And we get, for such devices, usually then a current voltage curve. So we draw now here the current versus voltage, and we get kind of diode curve, which is shifted here in the current axis. And you get here this curve, and the maximum power point would be roughly here where product of current and voltage gets maximum. This also means that this point here, which is the open circuit voltage VOC, is kind of important for these devices. So it's not just about harvesting these charges, but also harvesting them at a high energy. And the higher, in principle, this maximum power point, the higher the VOC, the higher also this maximum power point voltage. And this voltage is, of course, the point where we do not have any current flowing, because here the current is 0. This is when the device is at open circuit, we just measure the voltage. So at that case, of course, all the photogenerated charge carriers have to recombine. So this means the electron basically annihilates here with this hole, and in the best case, it emits again a photon. So that would be kind of the reciprocal process here to the absorption. This we call radiative recombination. This is kind of unavoidable. Any material that has this opportunity to absorb photons should then also, again, in the ultimate case, emit. And in reality, what we usually have, we have additional recombination pathways through defects, just symbolized here. This would be some state, for example, due to some impurity or some crystal defect in the material. This could also be a surface, etc. And this recombination usually is non-radiative, and this is an additional loss mechanism. So we want to avoid this loss mechanism. So we want to make solar cells which are highly emissive. So that's why in the end you can say the perfect solar cell is also a perfect light emitting device. That's why I want to show you from time to time here also some light emitting properties. Also this talk is about solar cell devices. And the idea is, of course, once you can control and understand these defects, you can make better photovoltaic materials and devices. So when we just quickly take again the ideal device where we have only radiative recombination, we can calculate the maximum power conversion efficiency as a function of the band gap. This is known as the Shockley-Queisser limit, so the band gap of the absorber. And in principle, you get such a curve which is decreasing for higher band gaps because we lose a lot of the solar spectrum due to transmission because we have a wide gap semiconductor, whereas here it is decreasing because we cannot efficiently harvest the energy of the high energy photons in this material. So this means that we in principle lose then in this voltage. And you see here some points for values realized for different technologies. And the perovskites, this is not completely up to date anymore actually. Like methylammonium lead iodide from aluminum lead iodide, or a little bit of mixtures, they have band gaps in the range of 1.5 to 1.6 electron volt. So already rather well suited because you can reach efficiency values in the order of 30%. We have now already, like the newest value I was just showing you in this NREL chart is here already at 25%. So there's a little bit of room still, but it's also already really close. And what we can do with this material as well, these are all these dots, we can tune the band gap. And this we can do by what people call compositional engineering. So in principle, one can partially replace, for example, the iodine here in our MAPBi3, let's say, by bromine. Then we can already get a much higher band gaps. One can replace, for example, the lead by tin as well and get lower band gaps. This A side has less effect on the band gap, only a little bit. And furthermore, this kind of approach of mixing compounds allows us also to stabilize entropically some phases, because not all the ABX3 compounds you want to make, let's say using these materials, really stabilize in the perovskite phase, because there are like geometrical considerations regarding this ionic radii, thinking of the Goldschmidt tolerance factor. But now I want to directly come to some measurements we did, and I want to discuss very briefly this radiative recombination here, which I said is kind of unavoidable because it already goes into the thermodynamic in this Shockley-Queisser limit. But what is important there is that you look at the absorption onset and that you have really a sharp absorption onset, because the Shockley-Queisser limit assumed in principle that at the band gap energy, we have a kind of heavy side function in the absorption. So above the band gap, basically all the photons with energies above the band gap are absorbed. But in reality, of course, we have always here some gradual onset. And in these perovskite materials, we measured those really at the, rather at the beginning of these devices. We measured like, this is now not the absorption, but it's the photocurrent response, external quantum efficiency in principle, or incident photon to current efficiency. With Fourier transform spectroscopy, so you can get it rather sensitive, and you can see that this absorption onset is really sharp. So we have an Urbach energy of around 14 milli-electron volt. And this then allows us to get rather high open circuit voltages. Because what we can then do, we can directly, knowing this absorption and knowing kind of the background radiation, the black body background radiation at 300 Kelvin. So when a device is in the dark, we can directly predict how the emission spectrum should look like, because it should in principle absorb this spectrum, and it should be in detailed balance. When the device is in the dark, it should emit, of course, again, the part that it absorbed from this black body radiation. And this is then in principle our luminescence spectrum. And you can calculate it like this blue line, and you can also measure it, for example, in electroluminescence. And this works very well. And why I was emphasizing that this tail is rather sharp. When you compare this to, for example, some organic solar cells which I've been working on before, these for sure are not state of the art nowadays anymore. But you could see if you just have kind of similar maybe absorption onset somewhere here at around 1.6 electron volt, all these materials or combinations are absorbing rather well. But then you have these additional tails which do not contribute much to the photocurrent, because this is a log scale here. But what they do, they reduce a lot the open circuit voltage which you can achieve in ideal cases, because you get a lot of recombination here in this tail. And in the perovskite, we start like with a radiative limit of the open circuit voltage. So that's the theoretical maximum if we take, let's say, methylammonium lead iodide. So band gap close to 1.6 electron volt, we can reach roughly 1.33 volt, whereas these devices, it goes down already a lot. So this is one of the advantages of this material. And the reason for these tails usually is related to disorder, for example. So there is not much disorder, at least resulting here in electronic states in this material. And if you make a donor acceptor junction, for example, in the organics, you get an additional here absorption and emission, then also feature due to the charge transfer state, which we don't have in the perovskites. And just to show you that these devices can really emit, we like to show this movie. Let's see whether this can also work in Zoom presentation. I think it did not really start. Then we can do with the picture. So here you see one of the solar cells we fabricated in EPFL in a holder and so on. But what you can see when we did not shine light on them, but applied an electric current in forward bias, we can indeed see their emission. And the emission spectrum, you have seen it before. It's almost, let me quickly go back here. It's here located almost already in the infrared, but you can still see kind of the tail which extends towards the red in this picture. So indeed, we are rather happy seeing like this electroluminescence even by eye in these devices. And nowadays, state-of-the-art devices, you can usually see it rather easily. And the question is, where does this come from? Why this material is kind of so emissive? Although we have like a nanocrystalline materials, we should expect lots of defects at grain boundaries, at surfaces. And one reason is what people call defect tolerance. This is illustrated here. So because we have, so we assume, let's say that we bring the constituents here of this material together. Here is a kind of classical case what you would have if you bring A and B together with these energy levels. You would see then interaction here, and you would then form new orbitals, bonding and anti-bonding ones. And in such a case, you would then have the bonding ones occupied, making the valence band states, the anti-bonding ones form the conduction band. And if in this case, you have, for example, some defect, meaning that you cannot make this bond, then most likely you will get states here in the band gap, because they will then probably be closer to this state or this state. Whereas when you have the situation like it is with the p orbitals of the iodine and the s and p of the lead in these perovskites, what you basically get, you see that this state here, which is the top of the valence band, that this results from an anti-bonding overlap here of this one and this one. And in this case, when you get some defects, like some vacancies, it is more likely that you form shallow states. And these states are much less detrimental for recombination, because for this defect recombination, states which are in the middle of the band gap are more detrimental because they can capture electron and hole with equal probabilities. And this makes them the highest, let's say, recombination, non-radiative recombination rate. So this was a kind of sketch how we can at least rationalize intuitively this defect tolerance in this material. And people try nowadays to use this design criterion to find novel optoelectronic materials. So how can we a little bit kind of quantify these recombination processes? For this, I like to show this graph here, where you can see again the open circuit voltage, which we are discussing now all the time, versus light intensity. Here would be then one sun. And these are calculations of what we are basically comparing here. So this line is the ideal one, the radiative limit, which I was discussing, let's say more or less very close to the Schoch-Licklider limit. And then we are introducing here in a very simple model, just here a defect which works as an efficient Schoch-Licklider recombination center, and we assign to this process just the lifetime of the charge carrier. So if this process is so fast that we have here, let's say roughly 1 nanosecond, we can only expect this open circuit voltage in the device. And we can see then it goes up and up. And what we can see that in principle, when we reach 10 microseconds here at 1 sun, we are already more or less very close to what we need. And people already are measuring kind of these values. And I just plotted here some symbols. These were devices which were fabricated at EPFL during my stay there, and starting from a mesoscopic device with still a rather thick mesoporous titania, and then going more to further engineered devices, not too much changing the device architecture, trying to engineer the composition and the position of the perovskites. We could really move, in principle, this curve upwards, and they follow actually rather well this very simple model here. But what I want to state is still that even in this device, we still have 99% roughly non-radiative recombination. So the yield is only in the percent, single percent regime, the radiative yield, so the luminescence we just saw in this picture. So there is still something to understand about this non-radiative recombination centers. And I just want to show a few studies where we try this more from the experimental side. So we try to make some devices, vary some parameters, and see how luminescence properties and how the open circuit voltage was affected. And for this, I just want to show kind of this cartoon where you can already recognize the radiative recombination, which we have been discussing already, which leads to the emission of photons. And also here you can see the trap recombination, which we have already kind of seen if there is a gap, mid-gap state here, and we can assign a certain lifetime to charge carriers there. And there might be other processes like Auger recombination, which is not so important for the charge carrier densities we are discussing under solar illumination. What is more important is it can happen that we get surface recombination, so that charges reach, I was discussing at the beginning, this kind of idea of making the device selective. But if, for example, our gold electrode here should collect holes, if somehow an electron reaches this electrode, gets extracted, then this is also a loss mechanism, which we call surface recombination, which needs to be avoided by making this interface as selective as possible by, for example, passivation measures and others. And we just want to see a few examples now. This is related to, let's say, to the grain boundaries first. And here you can see that in this study we made perovskite films. This is SEM pictures, top view, where we varied somehow the grain size by, in principle, changing the concentration of precursors in the solution. And what we can see when we plot versus grain size, or roughly estimated from below 100 to a couple of 100 nanometers. We could not see much. This is the current voltage curve normalized, but when you look here in this regime where recombination becomes important, when the current goes down and we approach the open circuit voltage, you can see there was in principle not much change. And also when we checked the electroluminescence, there was not much. So interestingly, and this is of course one key property of this material, that when you process it kind of right, that grain boundaries seem to be rather benign. And however, when we look, for example, at another case, these are impurities. Of course, many impurities do not matter in this material because it's not highly pure. But for example, when we get metal, some specific metals, like for example, gold, diffuse into this material, then we can indeed see that we form. So here you see again this kind of the absorption onset here of the perovskite, similar plot as I've shown you before. But now we look here more into the band gap here, so where we would not expect many states. But when we have this gold migrating, which can happen, for example, during degradation, during heating of the device, where we have here our perovskite, and here we would have the whole transport layer, and this gold can, for example, diffuse into here. And then we see a lot of these tail states, and we see a reduction of the open circuit voltage from around 1.2, for example, to below 0.9 volt. This is when it is in direct contact, but this is the example, for example, when it is degraded. And this can be seen here also when you look then at the current voltage curve of the device, which face this heat treatment. So for sure, impurities can be an issue, and we can then also try to measure the concentration, for example, or at least whether there is this gold in the material by TOF-SIMS measurement, where in principle dig into the sample and try to measure then the debris. And you can indeed see here, this is the signal from the gold. So indeed in this perovskite mesoporous layer, somehow after the heat treatment, this is the solid line here, some gold signal appeared there, which indeed shows that this gold entered the active material and served there as a defect. I want to come back to this JV curve again and ask a little bit the question how we can maybe better analyze this recombination. And there is one way, and this is trying to look, for example, at this open circuit voltage in more detail and investigate it, for example, temperature dependent and versus light intensity. One can write this kind of rather generic equation for the voltage, where we have here what we would call a kind of energy related to the recombination process. So this energy should in principle be, when we have these classical recombinations, which I discussed already, this should be more or less the band gap energy. So like here, for example, for band-to-band recombination, also for Shockley-Ritol recombination, where it goes through this defect state. But it could reach lower values, for example, if we have recombination at an interface, where we then have the electron, let's say, for example, due to this band offset here, sitting there, and then recombining with the hole here, let's say in our absorber material. Then you get here an energy which is lower than the band gap of the absorber. And when you do a temperature dependent measurement, you might have a chance to identify this. So this is the light intensity. The open circuit voltage scales logarithmically this light intensity, because we can in principle populate more and more the conduction band, so we can generate a higher electrochemical potential. And here we have the temperature included here. So the reason for a temperature dependence is in principle directly seen in thermodynamics, where you have to see that the electrical energy we want to get out of the system is entropy free, but the entropy also needs to be at least conserved. So there must be also some energy flux which contains this one, and this limits in principle this voltage. And this N is the ideality factor, and this can tell us a little bit on the recombination statistics, let's say. Unfortunately, this ideality factor turns out to be much more complicated than a kind of very simple way, because usually we would expect it to be, let's say, for example, either 1 or 2, and then also in between. And if it is 1, for example, it can indicate band-to-band recombination, but only also if your VOC is very close to the to this 1.33, or, you know, for a bit different material, 1.36. Also, I cannot even go here too much into detail. I would directly refer you to this publication, and also there are much more recent publications by many researchers in the last 1 or 2 years on this. Nevertheless, we want to quickly see here, for example, that it is possible when we compare two different devices, one where we have the complete stack and another one where we avoided the whole transport layer, this spiro, just to demonstrate the effect this kind of surface recombination, which we get here now, and this gold electrode will have on this ideality factor. First, we see that the open circuit voltage is already much lower. So we get a lot of loss here at this perovskite gold interface. Also, the gold might penetrate a bit, as I just discussed before. And we also see that the ideality factor is reduced from 1.8, in this case, towards 1.3. What we were doing here, we took in principle, when we go back to this equation, you can in principle see that when you do the light intensity dependent measurement, you can directly get this here from the slope here. And if the slope is not constant, then you can take a differential slope and you can plot it kind of. We also measure the light intensity up and down. That's why you get all these different curves. But at the end here, we can roughly see this difference in this ideality factors. So another question that is often asked from a kind of very kind of simple perspective is whether when we have this perovskite sandwich between these other layers, whether these energy levels are important and whether they might even, let's say, their positions of the material itself might even limit, for example, the open circuit voltage. When we have this titania, when the electron goes here, it will sit then, let's say, in this conduction band at this value, the hole roughly there. And then you can say, of course, I take this difference and I might claim that the highest obtainable voltage is in this case 1.2 volt. And from the discussions we had so far, this would be a little bit too simple, because we were saying that the open circuit voltage is defined by recombination. So, and recombination, at least at first glance, doesn't necessarily have to do something with these levels. So as long as I avoid, for example, that here in this case, the electron jumps up here, that the electron recombines with the hole recombined with an electron here. And this is not an additional recombination source. So this also means that itself, this value cannot limit the open circuit voltage, because the voltage is the electrochemical energy here in this system and not this potential energy here. And one can show this experimentally that these levels do not limit, at least directly, by using, for example, a bromine perovskite. You have a higher band gap, so we have a chance to get already higher voltage from the beginning. And you can get, for example, of such a system 1.5 volt out of the device, and we get actually nice intensity dependence, as we would expect from this model I was showing you a couple of slides ago. So the question is, when I was saying that this surface recombination might be a problem, whether one can try to kind of avoid it. And there is lots of research now going in this direction, trying to kind of passivate the effects, trying to put interlayers in between the perovskite and the whole transport layer material to avoid this kind of interfacial recombination. And here at EPFL, a postdoc, Marty, was also working on it. He was adding this kind of modulator into the spiral material, and with this one we could indeed get rather high open circuit voltage, so that this non-radiative voltage loss was only a bit less than 100 millivolt, and in this case these devices could reach real voltages in the order of 1.25 volt, and it was very easy then to see also the luminescence, and the quantum yield of our electroluminescence reached several percent in this device. We also tried to put, for example, some wide gap material like this PVP polymer in between those to see whether we can also avoid interfacial recombination, because also before we saw that dopants here, for example, in this material might influence recombination at the interface of the perovskite. So you want to have this kind of layer where maybe the holes can still pass through, maybe also tunnel through, and you avoid that electrons recombine. Here, maybe you might even expect some chemical activity here, which helps to really chemically passivate something. But in our case, we made many devices and there was a little trend. So with this modification, the voltages were a bit higher, but not that much. So then we said, instead of trying always to remove these defects or try to get efficiency higher, we wanted to see, well, when we add bulk defects to the material, can we really see a strong effect? And when we do this in a controlled way, what can we learn from this? And this is shown here. And I want to use this bismuth system later on to discuss some of the slow transients. So here you can see that adding through bismuth iodide bismuth in the parts per million regime, so this is referred in principle mole percent to the lead in the perovskite, we can already see that this open circuit voltage starts decreasing, and then it decreases a lot. And it comes along, this is the photoluminescence on a log scale, so it comes along with a strong decrease of the photoluminescence yield. So then clearly showing that this bismuth acts as a non-radiative recombination center in this system. And we try to further characterize whether we can also kind of detect somehow whether there are defect states. What we could see is that this bismuth can cause also shallow states. So again, I show you here this curve. We have here the absorption onset here of the perovskite. And when we add more and more bismuth, we can indeed see these tail states here again. And not as broad as for this gold, which I have shown before, but they are clearly there. And when we measure the surface photovoltage signal, also one can very clearly see a kind of increasing density of states here, tail states in the band gap. Also, we try to measure it with photoelectron spectroscopy, for example, where we measure, in principle, the valence states by using UV light, using the outer photoelectric effect, so to really eject electrons, and then basically from the kinetic energy we can then reconstruct how these valence states should look like. And also here it seems that we can get a kind of density of states. This would be like the band gap of the material, and we can see that something here is appearing when we add this bismuth as well. And talking about lifetimes, this I showed when I was discussing this theoretical plot of the open circuit voltage. Also, indeed, when we do transient photoluminescence, we can see that the lifetime decreases significantly from the microseconds to the nanoseconds regime. And interestingly, what we saw when we were adding this bismuth impurity to the devices, we also saw that in an impedance spectroscopy, which I cannot really explain in detail, but I want to try in a couple of minutes. Anyways, we saw that this feature appeared here, which represents what we call negative capacitance. Because here in this regime, we would have kind of a capacitive, here we have resistive regions, and when we go down here in this plane, in principle, it looks like an inductive response, which is not expected in such a material, and people often call it then negative capacitance. And this brings me then to the last part of this lecture, which are slow transient processes in this material, kind of really puzzling. They have been puzzling. They are still under investigation. And I have here 3 parts. One very brief kind of review on the hysteresis, because this is work has been done already a few years ago. And then I want to briefly give you an idea about this negative capacitance effect, and also what these slow transients, basically the impact of these transients on the long-term stability of devices. So let's come back to our current voltage curve. We discussed a lot here this open circuit voltage. Now we want to look here at the whole curve, and what people observed already really at the beginning of the perovskite research, solar cell research, that we can get what we call hysteresis here in the current voltage curve. So this is usually not expected. You just expect that you get like one curve which you report, and which is a kind of, let's say, a steady state curve at each voltage point when you sweep. But what people saw is that when you sweep in one direction, like here, for example, backward, and then here forward again, that there is this big discrepancy. And if you remember how we determine the efficiency usually of such a device, we look at the maximum power point, which is of course then different. So that's why it was of course very important, especially at the beginning then of this field, to at least measure correctly this hysteresis and then the power conversion efficiency, because otherwise you report kind of erroneous values. And interesting things, when you look at this hysteresis, I added a few more curves. It depends strongly on the rate. So it's a highly rate dependent process, because now you can see in principle when we go faster, like for example this red curve, we get very big hysteresis. When we go very fast, this yellowish curve, the hysteresis disappears again. So we can already directly say that there must be a process going on in this material, in the solar cell device, which is somehow in time scales, which are the times like we need to scan these JV curves when we do scans here in this regime. So when we do, let's say, 100 millivolt per second, so the whole JV curve takes us here maybe a bit less than a minute, for example. And for 10 millivolts, it will take us already several minutes, and here it is, of course, faster. And one of the explanations which was then in principle given, that this slow process is somehow related to defects, ionic defects in the material, which are mobile. So imagine that, for example, here we have our lead iodide. Let's say that this is, for example, missing. This would be a vacancy. And this would in principle be then positively charged, because the I minus here is missing. And applying electric fields, for example, this vacancy could move here around, and there was more and more evidence collected in the last couple of years that we have indeed all kinds of ionic defects which move around there. I just want to discuss a little bit what the impact of these moving defects then is on the current voltage curves, why it changes like it changes here. And I discussed already the scan rate. So this gives us an idea on the time scales we are discussing. And in this work, I tried in many kind of experiments to better understand what exactly is happening in these devices, to rule out, for example, capacitive effects, etc. And for example, what one can do here, one can, for example, stabilize the device at different points here and then do a very fast JV scan to, in principle, just isolate ionic and electronic contributions, and then you get a very different curves. And these curves are very much indicative that in the device something is changing regarding charge carrier extraction efficiency related to the electric field in these systems. And then there was, for example, the speculation that this effect is maybe mainly light induced, because the strong hysteresis you can observe, at least you can observe it much easier under light. And then you can do such an experiment, for example, where you just keep a certain voltage, like here we have, for example, this forward voltage, 1 volt, and then we suddenly switch back to minus 0.5 volt in this case and record the current transient here. And then you see that it's high and decreases, so this is consistent with this hysteresis, so that when we go back here, let's say when you come back, you have first a high current, and then kind of it has to decrease and you go backward. And as you can see here, it takes in the order of several seconds. And what you can do then, you can do the same experiment just in the dark and turn on the light later. Of course, you need to turn on the light, otherwise your current is very close to zero. then you can see that you in principle can just follow this trajectory, meaning that this process happened independent of whether the light was on or off. So it is clearly a voltage-driven process. And then we can come up with these kind of pictures as kind of try to summarize here. So the idea is when we have here our absorber, and we have here, for example, under, let's say, on the short circuit, or maybe we applied some negative bias. At least in this case, we even have a kind of gradient here in our some conduction band states here, meaning that there's an electric field, so it would drive the electron down here, the hole there. And if you assume that there are these mobile ionic charges, of course, they also see this electric field, and what they would like to do, they tend to screen the electric field, this material, similar to like electrons in a metal or ions in an electrolyte. And then we basically get low electric fields here shown by flatter bands here. And this is kind of illustrated here, then ions pile up there, and you can get a kind of dipole layer here. So this means, of course, and we then now want to kind of, let's say, do our JV sweep, and we want to extract these electrons, and now we suddenly apply forward bias, so we go towards open circuit voltage. We see that in principle there is, we can easily cancel this field if there is maybe there is no field, almost no field anymore there. So we directly generate an inverse electric field. In this case, we can only get these charges out if they somehow diffuse out in this direction. And this works only if the contacts are very, very well selective, so that they don't tend to reach the wrong contact. Because in case we don't have this selectivity, you would directly see this surface recombination. And when we do the experiment, we can nicely see this. This case is very much represented by this kind of S-shaped JV curves, because this diffusion is not so efficient here against the electric field. So we get this kind of S-shaped behavior instead of a nice JV curve here. And to kind of reproduce this effect in experiment, we just removed this titania, the compact titania layer. And then basically the electrode, in this case the FTO electrode, becomes much less selective. And then you can indeed see when we precondition the device here under, let's say here under negative bias voltage, we lose completely the rectification behavior. We get here just a curve which looks rather like kind of resistive. And this is because we lose the selectivity. So now just it's possible that in this case, that the holes can also reach the FTO, where we only would have harvested the electrons. And when you do dark curve, you can also nicely see kind of this shift here, but I just barely want to continue now here to quickly come to the last 2 points and showing what I'm showing here to kind of summarize this hysteresis effect, because you saw that we are measuring basically photocurrents, which kind of depended now on the biasing history, because we had this mobile ionic species. So this means in principle this is a rather complex phenomenon, because what we are measuring in this case at least is mainly the electronic response. So this is here all the photocurrent signal, and we see this hysteresis because this photocurrent, the recombination at open circuit, for example, I was discussing the surface charge carrier extraction, becomes influenced, for example, through the electric field by this ionic response. And these ions can also influence a lot surfaces and interfaces to the contact layers, for example, by forming dipoles. So we have many handles here, either on the ionic side or on the electronic response, to tune this hysteresis. So for example, if you have an electronic response which is less dependent on electric field, because you make a diffusion-driven device, because you have like highly conductive materials, for example, everywhere nicely selective contacts, then you might not see much hysteresis despite ions moving in this material. So no hysteresis or less hysteresis doesn't directly mean, for example, less ions or less mobile ions, because it could just be that your electric path was modified here in a way that it became less sensitive to these ions. And as a last example to kind of prove a little bit further these sketches, we had a collaboration with colleagues at the Max Planck Institute in Mainz, Professor Weber. He did KPFM on cross sections, so Kelvin probe force microscopy on cross sections of our devices. And by this measurement, you can measure the contact potential, and then you can reconstruct, in principle, how the electric field or the potential here is distributed over this cross section. And they did it in exactly a kind of experiment where they switched the voltage, this case from 0.5 here of such a hysteresis device to 0, and see how this potential changes. And this is then shown here. You can indeed see here that we have electric field here in our perovskite remaining for several hundreds of milliseconds before we then, and here you can see a trace here, before it then goes back to kind of the state which was there before the experiment. And this clearly indicates that there was somewhere charge piled up here in the system, and then slowly equilibrium is reached. Again, much slower than would be expected by like electronic charges moving in this material. So from this, I want to directly jump to this negative capacitance and at least give you a kind of idea, if you're not expert in impedance spectroscopy, how to understand this kind of puzzling effect. What I'm showing here is this Nyquist plot again, and we plot, in principle, we do impedance spectroscopy, so we measure, we set a certain voltage in the device. We can do this in the dark or under light, and then apply a small signal perturbation, so a sinusoidally varying voltage signal, and then measure the current, and from this we calculate the complex impedance. And we can then see in principle capacitive contributions which go up here and resistive in this direction. When we get several of these semicircles, we can assign some RC elements to them. So instead of plotting these semicircles, we could also make another plot where we plot, for example, there are all kinds of plots like Bode plot. I now want to, for example, plot the real part here, which gives kind of resistive contribution, and the imaginary part modified so that we get directly the capacitance. So we can, this is the same data just plotted in a different way, which I want to use and discuss now, coming back to this. So we have these two arcs here. So here there is so far not only positive capacitance. So we can, in principle, assign here an RC element, and RC means also a certain time constant to this material. So here first you see the RCs as a function of voltage. And what we can see here, we have this part here, this is for high frequencies. And we have this part here, which is then for low frequencies. And the dash parts are the low frequencies. So when we look at the high frequency, so this is blue is capacitance, and this is in the dark and under light. So we get here a rather constant value. This is what is kind of the geometric capacitance, just the solar cell, more or less the perovskite between the electrodes as a plate capacitor. The interesting point is these dashed lines, there you can see that kind of the capacitance here increases by several orders of magnitude when we go higher in voltage, and it is much higher also when the light is shining, when the light is on. At the same time, this resistance, following actually the resistance at higher frequency, so the when you compare solid line and dashed line, is decreasing by orders of magnitudes, which is in principle expected because it's a kind of diode. We are measuring, let's say, here in the dark, it is turning on this diode. So coming back to this resistance, we can, in principle, and capacitance, we can see indeed that for these low frequencies, we get these very high values for the capacitance, which are kind of not realistic. And the question is, where do they come from? And this is what I want to at least kind of give you an idea of here in this talk. Here you see again, in principle, what we have already seen. Now I want to say that instead of directly thinking here of a capacitance where you want to pile up some charge somewhere, it is already we discussed, better think that this is just a time constant, this RC. So we're just measuring some processes with a characteristic time, not directly something which maybe is like something what we would think of a resistance and capacitance. And then when we look, we can see here that this time constant for this low frequency component is around 100 milliseconds, and it is rather independent of both light intensity and voltage. And then already we can kind of understand when there is a time constant that is independent of these parameters, but we have a resistance which is strongly decreasing because the diode turns on, automatically there will be a kind of apparent capacitance which has to increase a lot. And this is indeed what we want to argue for. So you can see, for example, when we vary the scan rate of this device, when we go faster, we can indeed see that in principle the resistance here changes. In this case, the resistance when you scan faster decreases a little bit. And we can deduce this resistance here for fast and slow scan and plot here, for example, this resistance plot, and we can see that they nicely follow in principle. First, the different applied voltages, and then also like the fast one and slow one, in principle, this kind of frequency dependence of this resistance. And then when we just go to the negative capacitance, we can in principle do the same discussion. Now we get indeed kind of these negative features. And of course, thinking of a kind of RC element, we directly get a negative kind of capacitance there. When we plot the capacitance, you see indeed now this is the absolute value of the capacitance. It passes here through zero in these places and then becomes again really high and is negative here. So here comes basically the conclusion of this whole discussion now. And coming back to the idea that we are measuring just a slow process, what we did here, instead of measuring the device in the frequency domain, we just did the analogous experiment in the time domain, where we just kept it, for example, at a certain voltage and then applied a small voltage jump. And there you can see here that what you here is a zoom into this initial state. You see the typical capacitive response, right? You apply a voltage, you expect a jump here in the current, and then the capacitor gets kind of charged and current decreases and reaches its steady state value. And this happens here in the microsecond regime. So this is like standard capacitive response of the device. But then when you wait longer, we see that this current increases slowly again. And this, of course, an increase of current upon this voltage pulse means that this behaves like a negative capacitance. It looks like a negative capacitance. But this picture shows us already in these time scales that such an increase could just result, for example, from a changed resistance of our device, because we are operating here in a regime where current is flowing anyways. And this we can again try to measure when we just scan the current voltage curve and then take here differential resistance with different rates. So you can see that the resistance here for this device here, when we scan very fast, is higher because the resistance would be like the inverse of the slope here, than in this case when we scan more slowly. And then if you have this effect, it looks like a negative capacitance. But indeed, it's just a kind of apparent capacitance. So indeed, we rather change slowly the resistance. And how could you explain this? You could also try to explain this here. This is not just a qualitative sketch here, but also there is more quantitative models actually here in these references. So you could imagine that this device, in forward, you want to inject the electron, for example, but it faces an injection barrier here, an energy barrier. So let's say if you want to have from the titania the electron into the perovskite, which we need to do if you want to drive it in forward. And we have this barrier, and then we apply, for example, a little bit higher voltage. So there must be then some electric field. So making this injection a little bit more likely, but not too much. If we then assume again we have these ionic charges which move they should again screen the field here in this perovskite, and for example, by piling up here some positive charge there. And this positive charge can form here then in principle a dipole, reducing this barrier here and making it much more likely then that this electron gets injected. So we don't see that for this effect, we had to generate a kind of gigantic or a negative capacitance, but what you see is that we made this process more likely, which reduces the resistance slowly. And this is what we argue for, is the explanation for this kind of mysterious negative capacitance, also for the generally gigantic kind of apparent capacitance values. And we can see this also very nicely when we do JV scan starting at 0 volt and scan, for example, very fast. You can see that we do not here, when we scan slowly, we get a nice diode curve with rather low resistance. And when we scan faster, and this was an extreme device, of course, we can see that we get much less current into this device. So this explanation here, we did also temperature dependent measurements additionally, kind of is good evidence for such a model, which we proposed here. In the last 2 minutes or so, I just want to quickly discuss the stability of these devices. It is very well known that the perovskite is sensitive to moisture and also prone to photooxidation. So that is why when you monitor the efficiency versus time, here it's in hours, and when you have humid environment, they degrade very quickly. This was of course a very high humidity value, but also when you have here, for example, air where you have oxygen present, under light, devices degrade rather quickly. On nitrogen, like here in Earth atmosphere, it looks much better, but still there is degradation, and very often this is seen. Of course, there's also very good data reported in the literature. I just want to mention here that even when we have this little degradation in the inert atmosphere, so what we see here, like we measure for now 250 hours, we keep the device at maximum power point and record the efficiency. We see this decrease, but when we keep it in the dark, it recovers partially. So we end up in this point, and when we then cycle the device, turn light on and off, you can see that we in principle get a rather stable efficiency out of the device, because during the night, the device has the chance to recover, and one can try to analyze this as well. For example, again, using this analysis of the open circuit voltage, where you have here a pristine device and then a light soaked, where the VOC, for example, can decrease a lot. We try to do this extrapolation, and in this case, we see that during the light soaking, we introduced kind of new recombination channel, most likely at the surface, at the interface to the contact materials, because these effects, we usually don't see them when we just measure, for example, photoluminescence of film. Photoluminescence in this case would remain stable, maybe increase a little bit, but not decrease. That would be expected for this. So as a last point, which is then very application relevant, we said when we have all these kind of degradation mechanisms, especially these reversible ones as well, what will happen when we expose these devices to real kind of realistic weather conditions. Of course, you can do outdoor testing, but then you need to encapsulate the device very well, for example. What we did instead, we used meteor data from weather station like time, temperature, irradiance, wind speed, and plug this into our lab setup. And with this, then we could keep the device on inert atmosphere and measure the efficiency versus time. I just want to show here one example regarding this reversible effect. So what you see here, it would be a sunny day. So we see that here the light intensity goes up here then in the around noon it is highest, the temperature follows. This is here these red lines, and we compare this also to a silicon solar cell. And what you can see for the silicon solar cell, these blue lines, it has highest efficiency here in the morning and in the afternoon, and this is in the evening. And this is because of the temperature dependence, mainly because of this temperature dependence of this open circuit voltage, which we saw the equation just several times. And we can also already predict this behavior by just characterizing the device before. This is the dashed line. and then plugging in here this temperature and intensity data, and we can already predict it. But for our perovskites, you can see that the predicted line here, it's much less sensitive to temperature actually, because in this device there is also, like in our organic materials, there are charge transport limitations. So kind of higher temperatures, we lose a little bit in the voltage, but we might gain a bit in the fill factor, which is related to kind of resistive effects, which we can remove a little bit. And here you can see that the efficiency drops indeed. So, and this is this reversible effect. The next day it would basically go up again. So at least the devices which we have nowadays, these were like titania-based NIP devices. This effect would be really relevant in even operating those, and we actually measured many days during the course of a year. And at the end, we could make, for example, these maps here, which I was already mentioning, when we compare here silicon with perovskite solar cell during our weather experiment, the efficiency versus intensity and temperature. You can see here for the silicon that it is mainly here at the temperature that governs the efficiency. The colder and the higher, whereas our perovskite, due to the already mentioned kind of trade-offs, we are interestingly here in the most important regime with rather high values. This was already the last slide. Here is a brief conclusion slide. So I discussed a little bit the solar cell physics, focusing on recombination. I was saying that steep absorption onset and defect tolerance is key for the high performance of these materials. Then I showed some examples where recombination is happening, non-radiative one, like interfaces, impurities, and there is still more to do. In the second part, I discussed the slow transient processes due to this mixed ionic electronic conductivity of this material. And with this, I thank you very much for listening, and I'm happy to answer questions.